With that, I'd like to introduce our first invited speaker for the day, Cordelia, who's also, I guess, one of the top entrants for the contest. So,
okay, thank you, Robert. So I'll start off with presenting actually the results of the challenge. So first of all, what are actions? Actions are can be short actions such as the open handshake, or more recently activities such as the activities in the non-media detection data set. Okay, and so I'll start off with presenting actually the approach which allowed us to obtain the good baseline results of the challenge. Then I'll do a short evaluation of different components for human action recognition, and then I'll conclude the talk with an approach for modeling human-object interactions. Okay, so just what are dense trajectories? Dense trajectories, you sample densely in space feature points, you track them using optical flow, and then you design trajectory aligned descriptors. I most employ the NVH, which is the difference between optical flow, the derivatives of optical flow, which allow us to factor out translational camera motion. So it's robust to camera motion. However, it is robust to camera motion, but if the camera motion is more complicated, it's still not invariant to this camera motion. And so here, what we have added to the dense trajectories is to improve them by explicitly both estimating camera motion, the approach for estimating camera motion. What's new here is we combine different feature matches to have a dense map to estimate it well. And the second thing that is new is to remove the humans for the estimation, because the human actually induces incorrect feature matches. Okay, and here just overview. We have the flow, the human detector, feature points so we can calculate the homography below the flow, and then on the right, the corrected flow and the trajectories on the background, which are due to camera motion, which are removed. And so, in more detail, how do we estimate the camera motion? We find correspondences between two consecutive frames. We extract and match surf features, which are relatively robust to motion blur. And then we also use the optical flow. We take the most reliable points there, so points which have no information whatsoever removed. We combine these descriptors, surf and surf and red as a case like the optical flow. Then use mathematics to estimate homography. So it's all pretty standard. And here you can see the INRIA matches of the homography for a few examples. Okay, and then if you look here at these two examples, you can see here actually if you don't remove the human before estimating the homography, here that's the corrected optical flow map. You can see that the background motion is not correctly estimated correctly. That's true because you get a lot of feature matches which are incorrect, right? And then if you remove the humans, you can see that actually the optical flow, the correct optical flow map really shows the action of the background motion. The background motion is removed. And so here, what we show here is how do we walk the optical flow. We have a homography that allows us to walk the optical flow. And it improves for off, because there you really have the camera motion, but it also improves for MVH because the motion distribution is more precise. And then you can remove the background trajectories. And what's interesting here is two examples of failure cases. So if there's motion blurs are not integer, difficult makes estimation of matching very difficult because then you don't have any correct matches anymore, and then estimation fails. Okay, and then here a short video showing the results. So here you see the warped optical flow. On the right, removed trajectories. You can see it's not perfect, but it does generally allow to remove the background motion. You can see here also in these cases the human detector works pretty well. So again, it's something which human detector often works well, but in many cases it also fails, right? So it's not something which is completely perfect. Okay, and then if you look at the results, so what we do, we use the standard setting which we also use for still images. So apply feature vectors. Feature vectors have been shown to perform better than features for encoding image statistics, or here in this case video statistics. As with feature vectors, we also use power and THUMOS. Again, that has to show for static images to improve the performance. We also apply square rooting to the initial descriptors, which is again the trick which improves the performance by 0.5%. So these are all tricks which improve performance by a few percent, but they're all combined all together. It might be important to present the descriptors well. We've tested on different data sets, so how they look at HMBD, etc., and Ludwig sports. And so here are the results. What can we see? The first row is the dense trajectory features, and the different components are there. You can see, first of all, that both correcting the flow and removing the trajectories obviously helps to improve the overall performance. And if you look more closely, you can see that trajectory and HOF features are significantly improved. So here, for example, this is HMED. We can see here, if you look at the HOF performance, it's improved by 3 or 4%, by 10%, right? So minus 10%. That's clear. If you have optical flow which is not stabilized at all, it's not very representative. If you look at MDH, the improvement is significantly smaller, which is nice, which means it was really robust to camera motion, but of course it cannot handle all types of camera motion. It's also interesting, the combination of the two together further improves the performance, and that's because one measures the first order statistics, and the other one the second order, the zero and the first order statistics, right? So they're complementary. And if you look at HOG, again, intuitively what you would expect, that there's not much improvement. You can see that here, right? So from the warping you don't gain anything, and from removing the background trajectories you have a small gain, and that's what we do because we remove some of the unimportant information. Okay, and then here, the comparison, so here we use the combination of not the trajectory features. The trajectory features don't help with the combination. So here representing the combination of HOG, HOF, and MBH. Here the dense trajectories, here for the improved trajectories. First of all, we look at the improvement, compare the improvement for background features and feature vectors. Here are different data sets. We can see for background features and feature vectors, the improvement is consistent. So it does actually really help in both cases consistently to remove the camera motion. And what's nice here, we can also see that using the feature vectors consistently improves performance as well. So by using feature vectors instead of background features, we gain 2 to 5%. And background features we do use is not linear kernel, right? So it's not linear, same as linear kernel. The best settings for visual words, etc. And so but we can also see that for Olympic sports, where you have large camera motion, the gain is really massive. So here we have a gain of 7%, which is really significant. The smallest gain is for Hollywood, and I guess they're really the task of, yeah.
When you use an RDF expert, how do you process
So for the bag of words, if you don't use a chi-square quadrant, the performance drops by about, let's say, 10%. So there's a really significant drop. And for the feature vectors, you could also use it, obviously, right? And it's the discussion we had the other day with Iman over dinner. Anyway, so the feature vectors, the increase is about 1%, and the cost is enormous, right? So basically, given that you have this high-dimensional representation, your feature vectors are separable, and if they're separable, almost separable, you don't have to use nonlinear kernel, right? Yes.
I square over the
No, but you can use an adaptive. You can use an Euclidean distance, or you can use even get projector data to lower dimensions and use a metric, and then use a nonlinear kernel. Yes, I'm sure you can do it, but you agree if these features are high-dimensional, they're separable, right?
The fact that there's and I'm not allowing person, but the fact that you are saying that there is separable doesn't mean that you become the data very generalized.
Okay, it might generalize better, but if it's completely separable, then you don't need it, right? If you have a boundary which is completely clear, then you don't need it. And obviously, in practice, it's not 100% clear. So actually, we did run this experiment once, and there was a small gain there. Okay, it's actually true maybe for a challenge. If you want to win, maybe it's nice here. This could be another.
Yeah, tweaking on that other step. I'm just curious.
No, but it might be some idea of tweaking further. But I mean, it's very long, right? It's also with the 100 classes. If you have 100 classes, you don't want to spend. You won't have the training time to see if you can. Anyway. Okay, where were I? So basically here, okay, you can see that for I guess the smallest gain here, that's what I say, is for Hollywood, and so MVH is HMED is not so big either. Why is this so? Because the homography estimation for Hollywood is relatively difficult because there are a lot of humans in the foreground, and if the human detector fails, or even if there's a small stripe around it, you cannot estimate the homography correctly. I think that's the main reason. While for Olympic sports, it's like ideal for these kind of techniques. You really have a big background and you can really estimate the motion very, very well. And I guess you see sports, it's kind of similar. Okay, and then here, comparison to the state of the art. So in red are the best results from the state of the art. They're all from CVPR 2013. You know if there are any better results at ICC have updated it. And then we show the results with and without human detection. And so it's actually nice. You can see consistently for these 4 data sets, human detection helps. And we have also done in the figuring experiment, if you have a perfect human detector, the performance certainly increases a bit. So you can gain, it's not massive, but you can gain up to 3 or 4% by adding this human detector to estimating the motion.
So does it slow down? I mean, does it take about time to do all these human detection?
Well, the code I come back to that, but I can answer the question. The code we're currently having is like a pretty old version of some code, so it's very slow. So it does slow down massively. And so for our large scale experiments, we're actually not using it today. I think it's also it has been developed by some other students. So I guess the question would be, really, could you do human detection in real time? And I guess it's possible, right? It's something, it's one of the things that I've added in the conclusion, but I really want you to look into improving the human detector. So if we're having right now, it's not state of, it is, I would say, the state of the art and a bit slower, so.
Are you using human detection in order to suppress, so for example, the age of actions, there's some set that are voltage actions?
Yes.
Can you repeat the question? If you can repeat the question.
So the question is, if you suppress multiple humans, yes, you suppress multiple humans. So what we do is we have a human detector and then a forward and backward tracker. So you have multiple human tracks, and then obviously, as always in vision, there are thresholds and blah blah. So you have to obviously decide at which point you remove it, and you could also probably do something more probabilistic that you give higher or lower weights depending on the human response. It's something also we're not doing right now, and we're also not using the human detector. It's also something you could do using the human detector to further weight your features, right? Right now it's just used to estimate the homography, but you could also use it to rate the actions to really say that things which lie in the humans have a higher weight. Okay, and then, so this is just to come back to the challenge results. So here we use the improved trajectory features plus feature vector, so what I've presented so far. We don't use a human detector due to computational cost. Obviously, if you had enough time, you could have run it, but we just run that after the CPR deadline, and there was like 2 days to run the whole experiment, so they're actually running very fast. You know, we hit a knob and in 2 days the results come out, except for human detection. And what my student added was the spatial temporal pyramid to embed the structure information. So again, that gets you 100%. And it could work, but given that the layout of the actions are pretty different, we found that it's not something which improves performance significantly. Okay, and then we've also used the same approach in the TrackRead multimedia event detection challenge. I'll just show a few results. So what they're having there, one class is making sandwich, and this is the first. So if you rank all the results for the class making sandwich, this is the highest ranked one. This is ranked 20. And so all the ones between 1 and 20, they're correct. So what's actually nice is the first highest ranked ones, they're all correct. So even if the performance is not that good, the best ones are all ranked correctly, and so that's nice. If you look at the results, they're really very appealing. And then if you look at the first incorrect results, that's actually interesting. It's pretty clear why it's incorrectly classified, right? Because
So in this one, you didn't do the homography, human detection.
we do the homography, but not the human detection. So again, for TREG, there it's really too slow, right? So there you have, I must not matter, but 12,000 hours, I think, of video, and they're really already to extract the features and estimate the homography. The homography estimation and the feature extraction code we have now running very fast. So that's actually running well, but the human detection is not.
So that helps also in the
Yes. We're kind of right now doing exactly so. This year what we did, we added that and it gave us a few percent, right? So again, it gives 3 to 4% for TREG. So it's pretty consistent actually. So among the different data sets.
It's not clear that it's person detection you really care about in TREG. You really care about foreground motion removal. Like this is a hand here that's getting in the way. And the TREG videos are quite more sort of open source than action recognition.
Yeah, you're saying it might
Cars
not
moving in the
be.
background are going to ruin the model just as much as the humans moving in the foreground, right?
You mean that it might not even help that much, right?
Yeah.
So here another example for flash mob gathering. So again, you can see the highest ranked ones, they're all correct. And it's true if you think of a human detector there, it's really difficult, right?
Yeah, I can words.
But there are actually actions also where it would help, right? So for example, if you have moving an animal, so there you have one person performing an action, okay, then you should likely do it further and do something with the other objects, which is action as well. And then the first incorrect example is it's just a background video again, and you can see that here again, it's very similar in humans moving together, but instead of doing the flash mob gathering and moving to one point, you're just randomly moving around the campus. It's pretty clear where the confusion comes from. Okay, and so this was the first part of my talk, and the next part, so what we have also looked at recently is evaluation of different components for human action recognition. So if you look at the different steps of human action recognition, you have first the flow estimation, that is to run clustering, and then ideally you could also add high-level features. And so here, this would be the real optical flow, and this would be the perfect optical flow and the perfect masks and the perfect high-level features. And so what we have done, we have taken 21 actions from the HMPD data set. So one of the authors of the original data set is the author of this paper. We've selected a set of clips. The clips are a bit shortened, contain 30,000 frames. For each of these frames, you have annotated the human puppet, so you have actually the human outline. And so this gives you obviously the puppet mask, the puppet joints, and for the flow, you suppose that the flow between body parts is constant. That gives you an estimation of the flow. Okay? And then basically you have the estimation of the flow, you have this puppet flow. And then you can look, so here, the baseline would be without the trajectory features, and that's just features is not the motion corrected version. Then here are the results. If you had perfect optical flow, you would gain about 10%. And here similarly, if you just had the mask, no perfect optical flow, but you have a perfect mask, again, you can gain about 10%. That would be if you had a perfect human detector. And then here, if you use the high-level features of the joints information you have on the joints, then you get a 20% improvement. So if you had a perfect human pose detector, then you would get this 20%.
So 2D joint position, not 3D.
Yeah, you have the way everything.
So compared to this, if you just apply human detection of this more complex puppet model, then you don't get that much improvement.
Well, here, so for the mid-level features, we have compared using the bounding box and using the puppet mask, right? So that's in the paper. And you can show that basically using the bounding box, you get a bit less, but pretty similar to the mask, right? So,
He mentioned minority that
You can estimate them, right?
Clearly never happens to me.
Yeah, but he said, do you have 3D? And John is answering that he could probably get it out with the questions with his help. But that's another question. Yeah, okay, it's actually good. It's a good question. How reliable it would be, but given that already the pose is like artificial, given that we now know the 3D, it definitely makes sense. And so one question actually which we haven't really answered is actually why are we only getting 80%? So this is a subset, right? But why are we getting only 80%? Because given that we have now here perfect pose, we say maybe why don't we get just 100%? And I guess that shows that it's not just the motion which is important for human action recognition, but there's also some example. One example is climbing stairs. Climbing stairs obviously is very, very similar to walking, right? So if you look at the motion of the person, it's almost indistinguishable. So there you need to detect the stairs. Or another example is brushing hair. So again, if you don't see the hair, you don't know what the person is doing.
Even psychologists do experiment and show that they have just
Different actions probably.
Yeah, different actions. So the student actually didn't do a psychology experiment, but he showed the dots actually to students, to other students, and you cannot tell. So it's pretty clear that, I guess you can tell that for some actions, like for example walking, so they have these dot features with walking, that there it works, but for more complex actions, we looked at it, you cannot tell, and you cannot tell them apart, right? I think it's more, you cannot tell them apart. You know maybe that somebody is doing some movement with the hand, but you cannot say that, you cannot make a difference between fine-grained difference, right? Between turning a screwdriver, Siemens example, or turning an ice cube, you cannot have a difference between the two if you don't have the object, right?
Did you consider occlusions of some parts of the body?
So if you mean it, no, they're always annotated, right? So the examples are kind of chosen so that you can annotate.
They're all full body pose.
Or upper body more. So it's not full body, but what do you mean? Like if you mean I cannot see the arm, I guess then it's happening. So you cannot see the arm, for example, we annotate it still, but it's behind. You have this layer top of right? You can actually not. And I guess if you do the thing with the pose features, then you're not blocking the occlusion because you're just taking the joints and taking the relations. There's no occlusion term in there whatsoever.
How much more effort do you get the joint on the mask? What's the difference?
Well, here, what we have here is we have the joints actually, right? So here there's no effort because we annotate, we have a fully annotated body model of the person, right? So we just derive the flow, the mask, and the joint from that model. And the question is that this takes quite a lot of time to annotate, right? So somebody has to fit the puppet model to the human and then this annotates the joints automatically. We have a tool online to annotate these patterns.
Right, apart from the mask, the joint you have about 10% gain. What's the difference between mask and joints?
Well, the mask is just what you do is you just mask the image information and then you just take the standard pipeline, right? And you just extract from this mask region of the image you extracted and
There's
just
a standard human detection. Masking standard human detection.
standard human detector or a silhouette segmentation, and then you just apply the standard. So the question here is like what component, what would help most, right? It's kind of how much helps what. And so here you just mask out the image information and then you just apply its optical flow, right? And then its trajectory code as is.
I guess the comment is more that there's more information in the mask than there is in the pose.
Right.
So it's probably dependent on the features you're using. Like for example, you said that you can't tell someone brushing their hair from probably petting a dog or something like that with the pose.
Yeah, exactly.
But you could with the mask.
The mask is used just as a mask. Not as a silhouette description. You could obviously have a silhouette description on that, right? But here it's just used to take either the bounding box around the human to just take those features inside there, or you take more refined bounding box. And it's not at all, you're not extracting the shoe, you're not extracting silhouette. I'm using the silhouette for, because then it's exactly the same thing, but you have the silhouette. So yeah, you just that's more, if you could, that's what people have been doing, right? There's some papers about image salience, image salience. If you have something that indicates a trees salient, and this would be like the gauge that we expect, right? If you determine well which features are salient and you mask out the other features, that would be the gauge, right? And yeah, that's the suggestion, right? It's not silhouette, it's really mask operation, just like.
Okay, I have a look at that. Instead of putting the joint by hand, you may put it there. And you have that look at and the in the case.
Okay, so 5 minutes. So yes, you have seen that. So we have to improve current. So what we have to do, we have to improve current optical flow algorithms. So we have also done a preliminary evaluation with different state-of-the-art algorithms, and actually what's interesting is that the better algorithms for optical flow are not necessarily better for action recognition. So probably they perform a lot of oversmoothing. It's actually interesting. These several experiments, it just doesn't have to use, for example, the box and honeys. And no, and here, this paper uses another approach which does even more smoothing, the performance drops by. I mean, I don't know if you how relevant it is, we have to do more experiments, but it's clear that current optical flow techniques are actually they're not doing what we want for actions. And I guess also what you want for actions is that you have this relatively small things and you do over smoothing, maybe you just get rid of everything, which is significant, right? And then it's basically using the most basic algorithm, which is the optical flow for Fernberg, which is the OpenCV, gives actually results which are reasonable. And then second thing, I guess it's time now to move towards integrating using human detection and those estimation for action recognition. And so, again, we've done a very small experiment on a subset of actions where the actor is fully visible and applied the anagram and close algorithm, and actually there we show that it improves the performance by 50%. This kind of shows that if we manage to improve the close estimation a bit further, we're really there, and we can really use it now to improve the action recognition. Okay, then I just end with one video which I like. So this is kind of going into the direction that we need. It's already. Yeah, this is. Okay, so anyway, so the video. Okay, so this is just to conclude, basically, undermines the point that basically you should move away from just modeling the action, but you have to have also the interaction with the environment and the object. And I guess you have to move towards techniques which are relatively precise, right? So instead of just having a very crude context model, which is just a bag of features, you really want to have the interaction with the cup, and then you know the guy is drinking. And then you also can go further and spend a larger space, so you can say interaction with the cup, or you can give the history exactly the same thing, you can make a difference, right? Okay, thank you for your attention.
Couple of questions. I know people get interrupted all the time.
It's fine. You see at 101, you did not use, or you did use the human detection and the homography.
We use the mammography always, and we didn't use the human detection due to time constraints because we had to run it in a day or two of the CVPR deadline. So I guess it would be interesting now because if you have time, you can run it, right? Even if it's slow, it's not in the data set.
So you think you can improve it further if you use the human detection?
It would be interesting. So basically, for all the other examples, I showed that we gain let's say 2%, and if you gain 2%, it would be significant, right? If you look at
the 0.2% differences, so I guess 1 or 2% would make a big difference.
Yeah, and even if it's just 1%, it would make a difference, right?
Absolutely.
In the database itself, actually only including part of the body, for example, only feature ratio of the IRs, of the PIRs, and for that kind of machine, if you do human detection, you cannot find it. It's very difficult to find the human body.
What do you mean if you only have the upper body?
Yes, some can be smaller than upper body, because if you only have the face.
So the human detector we are having is actually, it takes different components. It detects the face, upper body, and the full body. And it's a
Okay.
combination.
Marker?
It's
Do you use a marker detector or marker detector? Multiple detectors.
multiple detectors. Yes. There are four components. Each one is transacted, and there's a
You train detector for different kinds of action, or use the same detector for all the actions?
We use the same detector for all the actions. It's just one standard detector, but it's assembled of different. And even the face trap detector uses the upper body model, the full body model, right? And we have the face detector integrated as well.
Okay, thank you.
Thank you very much, please, second speaker.